Okay, so this is an example to fit an AR2 model for a series with row 1 as 0.5 and row 2 as negative 0.84. The order of the model is always determined using a partial autocorrelation function plot, and the autocorrelation values are obtained using an ACF plot, or the autocorrelation function plot. So we have row 1 and row 2, and the model that we need to fit is xt is equal to phi1 xt minus 1 plus phi2 xt minus 2. And if we find the values of phi1 and phi2, we would have our fitted model. So if we recall the Yule-Walker equations, for an AR2 model, and the equations are row 1 equals phi1 plus row 1 phi2, and row 2 is equal to row 1 phi1 plus phi2. So we all know that this is a system of linear equations, and so we can't solve it directly by substitution and such, but putting it in a matrix form and solving it using matrices would be beneficial in terms of efficiency. So we have the values on the left hand side as 0.5 equals phi1 plus 0.5 phi2. I'm plugging in the value of row 1 and row 2, and I am going to change the autocorrelation over here to negative 0.38, or else the function, the series is not stationary. So negative 0.38 would equal 0.5 phi1 plus phi2. So in terms of matrices or vectors, I could write the left hand side as 0.5 and negative 0.38 equals 1, 0.5 and 0.5 and 1 multiplied by phi1 and phi2. So we'll call the vector on the left hand side as P, and this matrix as G, and that as phi. And we have to solve for the phi vector here, and phi would simply be equal to G inverse times P. So you have to use a TI-84 calculator to find the inverse of G and multiplying it by the matrix P and so forth. So on YouTube on how to find matrix inverses using TI-84. So assuming you find the video, I'm sure that there are plenty of videos online on finding the matrix inverse using a TI-84. The key steps here is define matrix G and P in the calculator. And find G inverse times P. So when you multiply, you would end up getting the value of phi to be 0.92 and negative 0.84. Now, the product here, you have to make sure that the order is preserved, in the sense if you don't follow the order and multiplying, you're not going to get the solution. So the order of the product matters. So we found the values of phi1 and phi2. So the fitted model is xt equal to phi1, xt minus 1, and phi2, xt minus 2. We simply have to plug in the values of phi1 and phi2 that we estimated. So xt is equal to 0.92, xt minus 1 minus 0.84, xt minus 2. And the next step here in this problem is to find the variance. So what is the variance of noise? So we have a derivation and the noise variance. Sigma squared A divided by 1 minus phi1 rho 1 minus phi2 rho 2 was equal to sigma squared x. In the problem, it is given that sigma squared x is 4. So 4 sigma squared A divided by 1 minus phi1 is 0.92, rho 1 is 0.5, minus 0.84 and minus 0.38. So a little bit of algebraic magic, and you have 4 times 0.2208, which is 0.8832. So this is a very simple example of an AR2 model. The key steps here would be to recognize the Yule-Walker equations, which have this standard format. You have 2 equations. It forms a system of linear equations. We rewrote the equations using matrices, and we plugged in the values rho 1 and rho 2 in the appropriate places here in the matrix P, or it's a column vector, and in the matrix G over here, and we made use of a calculator to execute that product, G inverse times P, and you would find the value of phi to be negative 0.92 and negative 0.84. So the first value would be the value of phi1, the second here would be the value of phi2, and the fitted model xt is that 0.92 xt minus 1 minus 0.84 xt minus 2, and the variance of noise, we simply used the formula that we derived in class, and we have sigma squared x given in the problem, which is 4, and plug in the estimated values of phi1 and phi2, we find the variance of the noise to be 0.8832, and that is a good place to stop.